Welcome to the advanced section of climate data analysis using Python. Let's start with the seasonal forecast. In this part, we will analyze seasonal forecast data on the go. Then we will look at calculating monthly anomaly. The data that we will be focusing on is going to be the NMME, seasonal climate prediction, which is a global forecast of 1 degree spatial resolution, and monthly temporal resolution with multiple months ahead forecast lead time. To make the analysis simpler, we will only focus on just one model. Let's go. Firstly, importing the necessary libraries. For example, import xarray as XR for handling multi-dimensional arrays. Import matplotlib. Import datetime for working with dates and times. Then import pandas as PD for data manipulation. Then select URL to the dataset we want to access. Next, open a netcdf dataset using xarray. Then print the dataset to inspect its contents. To make the data more descriptive and more convenient of analysis, we need to modify it first. Now let's convert a fixed start date to a pandas datetime object. Then create a new list of datetime object by adding the number of months to the start date. Then assign the new list of datetime objects as coordinates to the time dimension in the dataset. Then check if the dataset has a dimension named Z. Display DS. The above dataset has all the available forecast data for all lead times. We can now select our area of interest and limit the lead time to our use case. For this example, let's take a look at the temperature forecast for February 2021 that was generated at the beginning of the same month. For the loading data, we will use .load. Now let's plot the data and explore it a bit. Okay, now let's calculate the standard deviation of the forecasts among the sample numbers and then plot them for the entire globe, as well as only North America. Now you will create a graph with a specific size, then create subplots. Then set X and Y axis limit. Finally, adjust the subplots to fit into the figure area without overlapping. This is our figure. Looking at the above plots, we can see that uncertainty of the temperature forecast in the February 2021 is much higher across the northern latitudes than the southern latitudes. Now let's check if the forecasts indicate any significant cold anomaly for February 2021 across the Midwest US and southern plains. To do so, we need to load the climatology of GFDL forecasts and then find the anomaly by subtracting it from forecasts. In other words, anomaly equal forecast minus climatology. In the above dataset, S indicates the month index. We should adjust the coordinates of this climatology dataset and match it to the DS underscore cell that we prepared above. We will renaming the dimensions in the dataset, renaming X dimensions to lon and Y dimensions to lat. Then selecting data for February and dropping the S and L coordinates. Now let's calculate the anomaly by subtracting the climatology from the selected data. Then plotting temperature anomalies for each month. In a grid layout, color up equal 10. As it can be seen, most of the ensemble members of the GFDL sphere model correctly forecast negative anomaly for the majority of the Midwest US and Texas. Notably, this is the latest zero forecast, which was initiated at the beginning of February for the month of February. If we look back at late 1 or beyond, such a strong pattern and consensus are not found. Now let's begin with the climate change assessment using CMIP6 data. It would be really useful to have a quick exercise for analyzing climate change data. In this part, we will explore CMIP6 temperature projections from one model. We will look at monthly data for the historical period of 1970 to 2010 and future projections of SSP 585 during 2010 to 2100. Firstly, we will install GCSFS. We needed to extract CMIP6 data from Google Cloud Storage. Then import necessary libraries. After that, writing a CSV file from a URL and storing it in a data frame. Then display the first few rows of the data frame. Let's getting the length of the data frame, df. The df table includes information of all climate change model runs that are available on Google Cloud Storage. Let's narrow down the outputs to only those of monthly air temperature in historical and SSP 585 scenario. Next, filter the data frame to select rows where specific conditions are met. Then print the length of the filtered data frame and display the first 3 rows of the filtered data frame. Okay, much better. In summary, our CMIP6 search is narrowed down to 55 historical models and 35 SSP 585 future monthly temperature forecasts. In a recent climate change study, we should first evaluate the models during the historical period and then select a subset of models that outperform at the region of interest. However, since this is just an exercise, we will only choose one model that has data in both historical and future periods. Let's specify the climate model, which is GFDL CM4. Then get the Z store path for historical and SSP data for the specified model. After that, create a GCS file system. Then open xarray stores using the GCS file system object. Display DSHist. Looking at the metadata of the two datasets, the data period can be beyond our interest. Therefore, we can select our period of interest and then load the subset of data for more convenience in further analysis. But before that, the time coordinate is in object format, which we need to convert to date time to be able to easily analyze the time series. Now let's create a list of new time values for the historical dataset starting from January 15, 1850. Then creating a list of new time values for the SSP 585 dataset. Now let's assign new coordinates to the time dimension for the historical and SSP dataset. Then select the historical data from 1980 to 2010. Now let's load the historical and SSP scenario data into memory. Great. Now let's take a look at the average monthly temperature change over the globe in distant future. Firstly, calculating the monthly average temperature for historical data and for the SSP scenario data. Then calculate the difference in temperature between the future scenario and the historical average. Let's plot in the temperature difference for each month over a 30-year period. The difference for January, February, March, for example, is higher than June and July. And here's a plot of the annual mean change, mean temperature change between 2070 to 2100 comparing to the 1980 to 2010. For example, in the northern area, it reaches around 10 degrees Celsius. The above plots show that in an extreme scenario, SSP 585, the annual mean temperature in northern latitudes can be above 10 degrees warmer than the historical period, and the same for mid-latitudes can be between 5 to 7 degrees Celsius warmer. Please note that this is the result of one GCM realization at coarse resolution. In practice, these outputs should be first bias corrected and downscaled before further analysis. Now let's calculate the annual mean temperature for historical data. Then calculate the annual mean temperature change for the selected region under the SSP scenario. Then calculate the change in temperature anomaly. Finally, let's create a time lapse. Now let's make time lapse video for annual temperature change. To have a smooth video, we will plot the 5-year rolling average. Now we can have saved all the figures. We can use different libraries to generate a time lapse from the figures. We will use OpenCV here. Get a list of all files in the directory that start with the fig task change and end with the .png. Then sort the list of files alphabetically. Now let's generate simple time series plot. We can define a region of interest and explore the spatial mean of temperature change. For example, we will focus on the Northwest US. Then select and calculate the mean near surface area temperature for the historical period. Then create a new figure with the specified size. Plot the historical and SSP 585 data. Customize the plot by adding grad lines, set x axis limit, and so on. The blue line is historical data, while the red line is SSP 585 scenario. That concludes the advanced section of this tutorial.